Welcome to the second session in my 15-session statistics class. In this session, I'm going to talk about something that most people find boring, but I find fascinating, which is populations and samples. Let me back up. A population includes the universe of every single instance of an object or phenomenon you're trying to examine. Let me get to specifics. Let's suppose you want to see how businesses behave in the face of a crisis. Well, the population here includes every business on the face of the earth, right? Small or large, public or private, no matter where they are geographically. Now, that's going to be tough to collect data on. So you know what we tend to do? We look at a sample of that population. Last year, in the midst of COVID, this is one of the things I was trying to do. How are businesses coping with COVID? I looked at a subset. My subset was very big. It was every publicly traded company on the face of the earth, 46,000 companies. But those 46,000 companies are a subset of all businesses on the face of the earth. That's a big sample, but you can think of smaller samples that can be used, often to make judgments about how the population is behaving. Now, in terms of sampling, there are two ways you can sample data. The first is if you have data that is a time series. Again, let me give you an example. If you wanted to see how stocks do on a year-to-year basis, you can look at stock returns. And let's say you're specifically interested in the US stock market. You know, there's data on the US stock market that goes back to 1871. That might be the entire population, 1871 to 2020. But you might not trust the data before the Second World War or the First World War or before 1960. If you decide to look at only 2000 through 2020 data or 1960 to 2020 data, you're sampling. That's called a time series sample. Alternatively, let's assume you're interested in how much debt publicly traded companies in the US have. Again, there are about 9,000 publicly traded companies in the US. You might find yourself not trusting the data on really small publicly traded companies and look at only publicly traded companies whose market cap exceeds 10 million. That's a pretty low threshold, but you're trying to remove companies where the data is missing, there's not a lot of liquidity. It's called a cross-sectional sample. Time series samples, cross-sectional samples are both sampling examples. You're saying, why do we sample? Why don't we just look at the whole population? The first and biggest challenge might be practicality. If your population is either too large or some of it is inaccessible, you have no choice but to sample. In the US, every 10 years, the US government is required by the Constitution to do a census. The actual wording of the census is they have to count everybody who's in the United States at that point in time. Now, the US has 300 million plus people. Technically, the census requires that you count every single one of them. That's going to be almost impossible to do, even if the Census Bureau had unlimited budgets and time. But given that they have limited budgets and time, the census is based on samples. The samples are extensive, they're across the country, but you're looking at a subset of the population, extrapolating as to what the total population is and what its makeup is. The second reason you might sample is because it costs money to collect data on the entire population. There was a point in time where getting data on every US company would have been almost impossible to do it would have been too expensive to do. Today it's cheaper, but the costs of collecting data on the entire population might be such that you still collected only for a subset of the data. And the third reason is you might want to get results quickly. Well, we talked about one thing that one place you see sampling is in polls, before elections. Now, when you run a poll, you don't have the luxury of running it over 3 months because you want to get the poll results out quickly. Now, if you want to do something quickly, obviously you have to pick a sample. So next time you see a poll on anything, take a look at the size of the sample. It might be 800, 1,000, it might be 2,000, but they're extrapolating to the whole population, but they're doing it because they need to get results quickly. Practicality, cost, time. So sampling is more the rule than the exception. With that set up, though, let's think about the two ways you can do sampling. In a probability-based sample, you picked observations at random. In a non-probability-based sample, the researcher handpicks the sample based upon criteria he or she decides matter. So if I pick 50 or 500 companies out of the 9,000 publicly traded companies that are out there completely randomly, that would be a probability-based sample. But if I pick the 500 largest market cap companies, which is what the S&P 500 is, it's a non-probability sample. Now, if you think in terms of random sampling, there are actually three variants. In a simple random sample, here's what I do. I take the 9,000 publicly traded US companies, I pick 500 completely at random. The problem though with a simple random sample is I might end up with too many utilities or too few tech companies. So in a stratified random sample, here's what I do. I first break the 9,000 publicly traded US companies into industry groupings, and then I pick 5 out of each industry grouping. Let's say I have 100. I'll end up with 500 companies, but now at least I have a sample that's both random and covers every sector I want covered. Cluster random sampling is uncommon in finance and investing. But here's how it would work. I could take the 9,000 publicly traded companies in the US, break them down by letter of the alphabet with which their name starts into 26 groups. 26 letters in the alphabet. Then I'd pick 5 letters of the alphabet at random. A, C, E, G, and X. Maybe not X, you don't get that many companies. Maybe T. Now already you can see the problem with clustered random sampling. If I make the alphabet T, I take those 5 letters of the alphabet and I look at every company with that letter starting its name. It's a cluster random sample because the randomness happens based on the letters I pick, but then I look at every company within that with its name starting with that letter. The variants of random sampling. Now of course, while sampling is part and parcel of how we form conclusions, the one thing you constantly should be worrying about when you think about samples is bias. Why? Because when you have a biased sample, extrapolating your results to the population can give you some really misleading conclusions. And you're saying, but I would never be biased. I'm going to try really hard. It's really, really difficult to keep bias out of your sample because it can come from lots of different places. The first is exclusion. I'll give you a very simple example of how exclusion shows up. Exclusion is because a portion of the population doesn't even make it on to your selection criteria. So you don't even get to pick them because you don't see them. If I gave you the phone book, now including cell phones, if every person who lives in a town, you picked 100 randomly out of that, you said, I've got a random sample. Do you though? What about those people who don't have phones, cell phones or landlines? They won't be in the book. You've excluded them from your selection and therefore there's going to be bias. You sometimes have bias coming from self-selection when observations are derived from, when portions of the population are more likely to access your sample. I'll give you an example. Let's suppose you're a healthcare provider and you want to see how prevalent a bacteria is, and you set up clinics all over town where people can come in, or a virus is, and you set up clinics where people can come in to be tested. So you get 1,000 people tested in a day and you find that 250 carry the virus. Can you extrapolate then and say 25% of the population of that city carry the virus? I don't think so. And here's why. The people who self-selected, who came to your clinic, might have been people who were feeling a little sicker than the rest, or more likely to come to clinics than the rest. And as a consequence, that sample might not reflect the population. In some cases, the bias can come from you trying, but the respondent not responding. Again, let's talk about polls. Polls happen before elections, and one of the ways polls have historically been done, it's the pollster gets on a phone and starts calling people, and once they get to a sample size, they stop. One of the first problems they ran into is increasingly people started to drop their landlines, and some people had only cell phones. pollsters discovered that their samples were older than the population. Why? Because younger people were more likely to not have landlines. So pollsters have learned, they've added cell phones, they've added landlines. But in 2020, they ran into a problem, which is when they called people to poll them on who they would vote for, they discovered that those who were, who preferred one candidate rather than the other, I'm not in politics, I'm not going to name names, were refusing to respond to the poll. They were hanging up the phone because they didn't trust pollsters. That's non-response. And if you count them as not being in your sample and you count only those people who respond, you're going to be skewing your sample in favor of the other candidate, the candidate without the non-respondents. And finally, there is a bias called survivorship bias. Often when we think about a population, we think about who's out there right now, and we take the whole list and we sample from it. But what we miss is, if we're looking at something happening over time, not everybody stays in the population all through. Some people drop out. You think, what are you talking about? Now, one of the questions that research have been asking for the last 10, 20 years is, do hedge funds beat the market? And one of the ways they answered the question early on was they looked at hedge funds existing at a point in time, and they collected the returns on those hedge funds going back in time. And they discovered that the hedge funds that are around right now did earn returns that were higher than the market. You're saying, that proves that hedge funds make more than the market. You know what they were missing? About 25 to 30% of hedge funds don't make it, which is they don't make it. So if you take 2010 through 2020, looking at returns, not all the hedge funds that started in 2010 make it through 2020. Why? Because they don't do very well. In other words, your biggest failures often drop out. To study how hedge funds do, you can't just start with the hedge funds that are around in 2020 and work backwards. You got to go back to 2010 and look at all the hedge funds then, and allow for the fact that some of them don't make it, and the returns on those funds are going to be awful. It's called survivorship bias. Now, if you have bias, there are three things that can happen. One is that you blindly, you keep going. You're completely unaware of the bias, and that's when I think the biggest damage is done. Because if you're either unaware of the bias or you choose to be unaware of the bias, in other words, you push it to the side, then you're extrapolating to the population findings that are not appropriate. That's the most dangerous, I think, sampling bias problem. If there's sampling bias and you're aware of your problem, you can try to correct for it. Some of the pollsters last year, for instance, corrected for the fact that a large chunk of the non-respondents were likely supporters of one of the candidates rather than the other, adjusted the percentage of the poll that went to that candidate. It might not be perfect, but you're trying. And in some cases, there can be sampling bias. You might not be able to correct for it, but you can still use the findings as long as you state the findings narrowly. In other words, if I look at the S&P 500 and I discover that the companies in the S&P 500 are paying less in dividends now than they did 5 years ago. You know what I shouldn't be concluding? I shouldn't be concluding that all US companies are paying less in dividends now than they did 5 years ago. Because the S&P 500 is the largest market cap companies in the US. If I'm careful about how I state my findings, I should say that the largest companies in the US are paying less in dividends than they used to 5 years ago. So if there's sampling bias and there's nothing you can do about it, at least you can state your findings narrowly. That's bias. The other big issue in sampling is there's noise or error. Let me explain. I said we use samples to extrapolate to the population. And when you do that, you're going to do it with noise, with standard error. Why? Not because you haven't done your job, but because this is a sample. It's called sampling noise or error. And let me give you a very simplistic example of it. Let's suppose you have an unbiased coin. A coin, in other words, which heads or tails are equally likely. This is an easy one, right? So it should be 50-50 chance of 50% chance of a head and a 50% chance of a tail. You decide to do a sample of 100 tosses. At the end of the 100 tosses, I ask you, how many heads and tails do you get? Well, you might get lucky and get 50 heads and 50 tails, but odds are you might get 52 heads and 48 tails, or 46 heads and 54 tails. You're almost never going to get 50-50. That's noise. It's not because you didn't do your job, but because you have a sample. You think, how do you fight it? The answer is surprisingly simple, right? You take the 100 tosses, you make them 1,000, 10,000, 100,000. As your sample size increases, your numbers will converge on the truth. Your standard error will decrease. It might never disappear, but it will decrease. So here's the reality with sampling noise. It's part and parcel of sampling. It's part and parcel of statistics. Here's what you should be doing. When you sample and you're drawing conclusions, you should state your findings, but you should also be open about the noise in those findings, the error, the range in your findings. Because that's what your sample is conveying to you. So if sampling noise and error is part and parcel of the process, let's think about what we can do to reduce that sampling noise. Now, before we look at things you can do, though, I'm going to introduce two words into the lexicon here that you will often see in the context of sampling and statistics. The first is the word independence, and the second is the word identical distributions. In fact, they're bunched together often, and samples are checked for IID, the first I standing for independent, the second, the ID standing for identical distributions. But what do they mean? Let's start with independence. Events are independent, where whether an event occurs or not is not a function of other events happening. Again, let's start with a simplistic example, a coin toss. I know it's an example we keep coming back to, but it's the easiest sampling example to think of. Now, when you toss a coin, assuming it's not a biased or a skewed coin, whether you get a head or a tail on this toss has nothing to do with whether you got a head or a tail on the previous toss. That's pure independence. In contrast, let's think about something we do in investing all the time. To decide how much we will make as returns on stocks next year, we often look at historical returns on stocks. In the US, that historical database goes back almost 100 years, have returns every year for the last 100 years. Now, are those returns independent? The question I'm asking is whether what will happen in the market in a particular year has anything to do with what happened in the previous year. Put simply, if stocks went up a lot last year, does it have any relevance to whether stocks will go up, go down, or do nothing this year? Now, that's open to debate. In fact, it's empirically checkable. But there you can see the assumption of independence is already more difficult to make. That's independence. What about identical distributions? Now, each event has to draw from a probability distribution, and if you have identical distributions, you want every event in a universe to draw from the same distribution, or at least in the sample. So again, take coin tosses. Every single coin toss draws from the same distribution. It's 50-50. It's identical distributions, meets the test very easily. But what about stock returns? I'm looking at annual stock returns from 1928 through 2020. Now, the stock returns in 1928 drew from a distribution of returns that year, and that distribution reflected the economy then, the market then, investors then, companies that were listed then. You can already see that assuming that same distribution works in 2020 is quite a stretch. Stock returns are probably neither independent nor identically distributed. And I'll make this broader. In finance, researchers, investors, analysts often assume independence and identical distributions because it makes life simpler for them. It allows them to draw strong conclusions. But the reality is, finding either is really difficult to do in finance and investing. Now, I think, why do you care so much about independence and identical distributions? Because it allows me to use my favorite law. In fact, it's really not a law, but statistics, it's called a law, called the law of large numbers. Basically, here's what it says. Remember, when we create samples, it's to come up with findings that we extrapolate to a population. The law of large numbers states very simply, as the number of observations you sample, as your sample size gets bigger, your sample average will approach the population average. That's very powerful because it means I can take a sample of 1,000 and what I get as an average for the 1,000, I can extrapolate to a population of 100,000 or even 10 million. But the law of large numbers applies only if observations are independent and identically distributed. Now you see why I spent a little time on that. So there are two exceptions to the law of large numbers. If the sample observations are not independent or identically distributed, you have a problem. The second is for distributions with fat tails, lots of extreme outcomes, the law of large numbers might not work. Now, before you give up on the law of large numbers, there's a weaker law called the weak law of large numbers, which says that even if your sample is not, contains observations that are not identical or not independent or identically distributed, the sample average will still approach the population average, albeit at a slower rate than if you had both independence and identical distributions, as long as the variance is finite. What does that mean? Well, in some cases, you can have distributions with infinite variance, and there even the weak law of large numbers will fail. Now, in finance, we're really drawing on the weak law of large numbers, not the strong law, because as I noted, finding independence and identical distributions is really difficult to do. Now, the end game here is to take what you get from the sample average and make statements about the population. I'm going to leave you with two final propositions, theorems, whatever you want to call them. The first is called the central limit theorem. And here's what it says. Even if your population distribution is not normal, if you draw a sample from that population, the average you get for the sample can still be normally distributed. And the nice thing about that is normal distributions come with a great deal of power. You can make statements about what can fall within 2 standard deviations or 3 standard deviations. So the central limit theorem says even if your population is not normal, it has a different distribution, you can draw a sample from that population and make statements about the population based on the means of the sample, which are based on a normal distribution. We do this all the time in statistics, and it's in fact a very, very, very powerful statement. Now, even if you don't buy into the normal distribution being the end result, there are broader statements you can make. In statistics, there's a finding called Chebyshev's inequality, which says even if you have a distribution that's not normal, you can make general statements about where most values should fall. So even in a non-normal distribution, about 75% of the values must fall within 2 standard deviations of the mean. So if I told you the average height across 100 people is 5 feet 8 inches, and the standard error on that, on that estimate is 4 inches, I can make statements about how most people in the population are going to look in terms of height, based upon the fact that most observations have to fall pretty close around the average. So both the central limit theorem and the looser statement about Chebyshev's inequality allow you to make statements about ranges that you could not make in their absence. So let's sum up. In statistics, we sample constantly. Sometimes the samples are random samples, sometimes they're non-random samples. The reason we sample is because it saves us time, it saves us money, and sometimes it's the only thing you can do. We take those samples and we derive numbers from those samples that we extrapolate to the population. And if the population is composed of observations which are independent and identically distributed, then we can make very strong statements based on our sample findings because of the law of large numbers. But even in the absence of independence and identical distributions, you can still make statements about the population, but your sample size will have to get much bigger. So that's the bottom line in sampling, and we will talk more about the statistics we get out of samples in the coming sessions. Thank you very much for listening, and I hope you found this session useful.